Hey, year 10s, thanks for coming along, guys. Right, so everything should hopefully be working fine. Yeah, no, Ian was first on the chat. Well done, Ian. Right, so I'm just waiting for my YouTube channel to catch up with me. I've been going, it's also nice for me to know the delay. It's about 20 seconds. Yeah,
Ian was first on the chat. Well done, Ian.
There we go. So I'm now going to pop out the chat window. Pop out chat, pop out chat. Get rid of that now. There we go. And let's crack on with simple covalent. So share screen. I've got no clip cam today because I'm in school. There we go. So I can just get rid of my face entirely. Right, and on to this. This is the very last lesson of GCSE bonding, and it is on simple covalent. So 3 learning objectives today, folks, that match my YouTube channel. You might realize, by the way, that my YouTube lesson was scheduled like a month ago. It's hilarious. So 3 learning objectives. Number 1, understand the low melting point and boiling point of simple covalent. Number 2, understand the size of molecules affect WIMFS. And the last one is be able to predict melting point and boiling point trends. So, okay, so we've been doing covalent bonding. We did graphite last lesson. We did the giants. And we talked about how the giants have these insanely high melting points. And I said that you need to learn your giants. There aren't many of them. So what that means is once you've picked up your giants, so it's nice just to remind us of our giants. Yeah, our giant covalent compounds or structures or elements are diamond, graphite, diamond, carbon solid as diamond. Yeah, and it has that cool little pyramid-like structure. Carbon solid in the form of graphite, which is very special, forms in layers. Yeah, those layers can slide. Each carbon atom makes 3 covalent bonds. The 4th unpaired electron can become delocalized and flow between the layers. Remember graphite and how special it was. Then we had silicon as an element as well, which has exactly the same structure. That's silicon, by the way. And that has exactly the same structure as diamond. Then we had silicon dioxide, which is otherwise known as silica or sand or quartz. Yeah, sand, quartz, all the same stuff. Silicon dioxide, proper name. And then we had titanium dioxide as well. And that basically summed up your giants. We then talked about our graphite derivatives, but in a sense, those are your 5 that you really need to just bulk learn. And therefore, anything else that's non-metals is simple covalent. So the first thing we need to make a note on there is that. So facts for simple covalent. Or simple, by the way, you don't need the word simple. Yeah, what it should be is facts for covalent. Because there are so few giants, the word covalent applies immediately to the simples because most things are simple and not giants. So facts for covalent substances. Number 1, made from non-metals. Made from non-metals. Made from non-metals bonded to other non-metals. Yeah, let's look at an example of these. Yeah, e.g. water, H2O, is all non-metals, therefore it's going to be simple covalent. I'll just put simples. Simple covalent. You realize the simple doesn't really need. Let's look at another one. Hydrogen sulfide. Bad egg smell, by the way. It's not nice stuff, that. That is also simple covalent. Yeah, all non-metals. Let's go for another one. Carbon dioxide. Simple covalent. Yeah, let's look at another one. Sugar. There's a great one. C6H12O6. By the way, that's actually glucose, if you're interested. Yeah, that's actually glucose, not sugar, because the sugar you put in your tea is sucrose, which is actually a disaccharide. I think made from a glucose and a fructose, I think. But that's glucose, and this is simple covalent. Yeah, we get used to this. If you see all non-metals, you're probably simple. Okay, next fact. Fact number 2. This is fact number 1. Oh, fact number 1 fact number 2. So fact number 2 is they all have low, and notice my capitalization, low melting points / boiling points. You can't do this, by the way, in your exam. You need to actually write down melting point or boiling point. Yeah. Now this is strange. This is an odd thing, because if we have covalent bonds, we know from a previous lesson, covalent bonds are, this is a covalent bond, a stick. Covalent bonds are insanely strong. Insanely strong. So why would they have low boiling points? The reason being is because fact number 3, within the molecules are, notice my capitalization, strong covalent bonds. Strong covalent bonds. Let's have a look at the picture. There you go. I wonder if anybody on the chat, please, what is the shape of water? I wonder if anyone can give me the bond angle as well. What is the shape of water? So within the molecules are strong covalent bonds. These are strong covalent bonds. Yep, but, and this is the big important bit, but. This is a big but, folks. Yeah, but between, notice my changing color. Please do the same. Oh, check out Zyna. I'm impressed. Water is indeed, the shape of water is bent, and its bond angle, well done, Zyna. It's 104.5 degrees, just for fun. It's nice to be able to, I love that you know that. So, but between the molecules are, and this is important, weak intermolecular forces. Now, I like to shorten this, by the way. I like to shorten it. I bet you can figure out what I'm trying to spell. WIMFS. Between the molecules are WIMFS. Now, you're not allowed to use this in your exam. Yeah, you have to translate to weak intermolecular forces. Yeah, but it's just easier to remember WIMFS. Yeah, so between them, and what does this now look like? It now looks like this. A new picture arises. So we now have water with covalent bonds within it, but between the molecules, I have now got WIMFS. And that is a weak intermolecular force. Don't need the dot. And these are what we break. So when is van der Waals and WIMFS the same? Zyna, you definitely don't need that yet. I try to avoid that as best as possible. Van der Waals is one of the WIMFS. So just as a spoiler, thanks to Zyna, at A level, you learn that there are 3 WIMFS. Yeah, and one of them is van der Waals forces. Yeah, but you don't need these at GCSE. All you do is call them weak intermolecular forces. You don't need this at GCSE. So I'll just leave it as weak intermolecular forces. And these forces are very weak. What that means is the energy to break these, so we can then do a nota bene, even an exam question. So let's do an exam question. So explain why water has a low boiling point, brackets, 100 degrees C. Yeah, so, and then what we're going to do is, now as soon as you see explain boiling point, we know what we're running. We're running Susan Boyle sings Nelly the elephant. Yeah, so what is the structure? So the answer to this in green, water is a simple covalent. You don't need the word simple, but you can put it in if you want to. Water is a simple covalent structure. Covalent substance. Structure let's go to the structure. Is a simple covalent structure. Bonds between the molecules. Between the molecules are weak intermolecular forces. Yeah, you can't write down the word WIMFS, but you just translate the word WIMF out. Next, strength. These are very weak. There has the word weak in it. These are very weak. Number, there are very few. There are very few WIMFs. I'm just adding on the WIMFs. Yeah, these WIMFs are very weak. There are very few WIMFs. You don't need to say WIMFs every time. I'm just saying it just so I'm just reinforcing the WIMF, trying to say it as much as possible. But there are very few of these forces. That would be absolutely fine. So the energy to break WIMFs is low. You're done. Okay, so this is really all we need to do. But what we're going to now do is, so we can now at this point go to my learning objectives and go, right, we can now explain and understand the low boiling point of simple covalence. We know that there are WIMFs between the molecules, and these are weak, so it doesn't take much energy to break them. Now we need to do the second one, size of molecules. So let's do a couple of, I'm tempted to, well, okay, let's keep going. So we can do a little subheading. Don't want to rush people, by the way. God, that's an important question to do, isn't it? You're not breaking covalent bonds. Oh my goodness. To break those covalent bonds would take 2000 degrees Celsius. Yeah, we're breaking WIMFs when we boil water. It's nice to draw the picture, by the way. So in a kettle, I could do a better kettle than that. In a kettle, there we go. In here, what we've now gotten, there we go. In our kettle, we have the water molecules, which I'll do in blue. The water molecules are like this, yeah? And between those water molecules, it's all random because it's a liquid, yeah? There's no gaps, by the way, between them if you ever draw a liquid diagram. That's a terrible liquid diagram, by the way. At GCSE, you have to be able to draw liquids. And liquids, there are no gaps. Yeah, this is a liquid like that. There you go. No order to it, but still touching. Yeah. So, but now we get this new picture. These are the water molecules. And let's now show the WIMFs. Yeah. Let's now show the WIMFs like this. I just think it's a bit thick. I can make that better. These are the WIMFs. Covalent within them, but WIMFs between them. There we go. That'll do. So, if you like, we could go covalent within. Too small. I've gone too small. Oh no, there we go, it's fine. So covalent within, but these dotted lines are WIMFs. These are weak I'm not going to bother. These are the WIMFs. Right, so when we now apply heat in our kettle, yeah, we've got our heating element, and we apply heat to this. What happens is I break the WIMFs. The water molecules are not broken. Yeah, the water molecules are not broken. They are simply breaking the WIMFs. I'm trying to make it as small as possible, and I can't. Still water. Yeah, still water, just no more WIMFs. And those WIMFs don't take much energy to break. Yeah, so that's actually such a useful diagram to understand. Yeah, so we realize that the circles contain the water molecules with covalent bonds. These are not being broken. What we're breaking is the WIMFs between them. Okay, well, I really like that diagram. Wow, that's like the world's tiniest diagram. Yeah. Yes, that's better. Excellent. So that's what's going on. So let's now do size of molecules. Yeah, I'll make my pen a bit thicker. Size of molecules. So the next thing we need to learn is really easy. And that is that the bigger, try that again. The bigger the molecule, the stronger the WIMFs. The stronger the WIMFs. So what does this mean? So we can now look at some molecules here, and what I'll do is I'll try to keep them within the family. So let's do group 7, love group 7. Yeah, so group 7, the brackets on the chat, please. What's the family name called, please? So we've got fluorine, we've got chlorine, we've got bromine, and we've got iodine. We don't bother talking about acetylene. What's the family name, please? Right, so let's now have a look at the molecules that we see here. Yeah, well done, Zina. Zina's the only person contributing on the chat at the minute. Be nice to see more people contribute on the chat, please. Yeah, thank you. So they're called the halogens. So let's have a look at what these look like. Thank you, Gayatri. Well done. So fluorine looks like this. Here's fluorine. 2 electrons in the first shell. 7 electrons in the second shell. And it stops, and then it links together with another one. Links together with another one. Oh, I'll do that one as dots. Just to be good about my Lewis dot and cross. I'm even going to put my little dot and cross in the gap. There we go. So there's fluorine. So thank you, Julius. Thank you, Callista. So what does chlorine now look like? So by the way, fluorine is a pale yellow gas, but in reality, you're allowed to just call it colorless. Yeah, colorless. Let's now go to chlorine. So chlorine now looks like this. First shell, 2 electrons. Second shell, 8 electrons. Third shell, 7 electrons. Right, so what we realize is happening, oh, come on, Mr. Duncan. That's better. So chlorine now has 7 electrons in its outer. It pairs up with another chlorine. This is where what I'm going to do is, no, I'm just going to do it. Come on. That's better. That wasn't bad at all. Take off those guys there. Put the dot and cross in the gap. Yeah. Chlorine is physically bigger. It's just larger. Way larger. Yep, there's chlorine. So this is a green gas. Green gas. So the molecule's getting much bigger. Let's now look at bromine. First shell, second shell, third shell, fourth shell. Bromine's now absolutely massive. It's huge. I'm not going to go all the way with bromine. There's not really much point. It's only because I'm going to freak people out and I don't really want to do it. But here's bromine. Yeah, try and make that the same size as the other guy. There we go. So bromine is now larger. 7 electrons in its outer shell. If you want to know that there's 18 in the third at this point, but you don't need to worry about that. The point I'm trying to get here, guys, is they're getting bigger. Now, what that means is that if you were to have a look, you can now, based on this one fact, the bigger the molecule, the stronger the WIMFS. So who's going to have out of this group is this for A level 2? No, it's not. This is GCSE, Sasha. This is GCSE. I have done a complete set of bonding lessons, Sasha, on A-level chemistry on my channel. So if you go to my videos, you'll be able to track down the A-level bonding lessons, I believe, that are there. Have a look at those. So bigger molecules means that there's going to be stronger WIMFS. The fluorine WIMFS are very weak, but then the chlorine WIMFS are stronger, but then the bromine WIMFS are stronger again. So what this means is the boiling point increases. Yeah, it has the strongest WIMFS. Yes, correct. And by the way, that's actually, Jack, your sentence there is perfect. You're saying it has the strongest. You can't say the word strong WIMFS because that is literally that's opposite of what this is. Strongest or stronger. Yes. So the bigger the molecule, the stronger the WIMFS, the higher the boiling point. I'm just for Sasha. I know she's probably already left already by this point. It'd be nice for me to be able to actually. No, it's okay. I'll stick with this, and then yeah, if you go to my channel. I believe they're there and they're ordered as well. I'll put them in a playlist for you, Sasha. So bromine's going to have the high, and iodine. So we now get fluorine is a pale yellow gas, a colorless gas, but it's pale yellow gas. Yeah. So this is a gas, and then we get our green gas of our pale green gas of chlorine, and then we get our brown liquid. We get our brown liquid of bromine. Brown liquid. So it's become a liquid. The boiling point's increasing. And then we end up with our gray solid for iodine. So the boiling points are increasing simply due to, and they'll ask this, they'll say, here's the exam question. Explain why the boiling point of group 7 increases down the group. Okay, so answer in green. Yeah, answer. As you go down, bullet point number 1. As you go down group 7, the molecules get larger. I can even give you like a fun thing in terms of their mass if you like. So fluorine, which travels around as F2, the symbol for fluorine is 9 and 19. Yeah, and it's traveling around in a pair. So its relative molecular mass, yeah, its MR is equal to 19 times 2, which I can't do in my head, 38. 19 times 2. So the MR is 38. If you look at chlorine, Yeah, chlorine is Cl2. Well, we know, by the way, it's nice for me to actually tie in the correct thing there. Yeah, the 19 times by 2. So chlorine on the periodic table is 17 and 35.5. So we now go, but chlorine is in a pair. So 35.5 times 2 gives me 71, a relative molecular mass of 71. It's getting bigger. They're physically getting heavier. Bromine, holy moly, now I'm going to remember symbols. Bromine is element number 35, and its relative atomic mass is 80 times by 2. The MR for bromine, this is big now. It's 160. And iodine? I'm not going to get iodine correct. I never deal with iodine. I never usually get down to this size. Iodine is element number... Oh no, give me a sec. 52? I don't know. Hang on a minute. 53. It's element number 53. And its mass is 120 something. 127? I have no idea. I've forgotten. Oh no. GCSE. 127. Yes! Nailed it. 127. Yeah. So an iodine in a pair. I got way too excited then. The MR is 254. The size of the molecules is increasing. Yeah, size and mass increasing. Do you see how amazing the periodic table is? I can't believe I got it right. I don't usually get down to that size, if I'm honest. I'm surprised. It was a guess. So they get the size and the mass is increasing. So second bullet point in the exam. So the weak intermolecular forces are getting stronger. With increased size of molecule. Stronger, remember, they're not getting, if you say strong WIMFS, you're dead, because you can't have strong, weak intermolecular forces. That doesn't make sense. Stronger, yes. And then you always go back to energy. So more energy needed. More energy needed to break WIMFS in iodine compared to fluorine. Just give an example. More energy to break WIMFS. That's it. So that's all you've done there. So it's a really clever trick. We can do this. So it's nice to use the halogens as an example. Love the halogens. So let's do another one. So since we've now done that, what I'd like to do is I'm going to give you some questions on the chat and see how quick you guys are on this. Question number 1. Let's do methane. This compound here is called methane. Methane versus propane. Double it and add 2. 8. Propane. Who has the higher melting point? I'm going to say higher MBT? Question mark. Go on the chat, please. Question number 2. Let's do hydrogen. Oh, that's a tricky one. No, I won't do that one. Let's do glucose versus sugar. C12H, got to be careful here, 22011. Do you also have videos on Unit 2 as chemistry? And is this a good recap? Sasha, so yes, I do have lots of Unit 2 videos. I'm sorry that I haven't put them into as many playlists as I should have. Yeah, this is a good recap for GCSE. Yes, definitely. For weak intermolecular forces, absolutely. And yes, there's loads on Unit 2 on there. I will, do you know what? I will endeavor to try and put them into playlists for you. Since she's there, just to show her my channel, if YouTube. So, really quickly. So if I go your channel and go to videos. So I've tried my best to number them as best I can. So there's AS halogens, AS organics, shapes, there's bonding. So AS shapes lesson 2. AS bonding should be on here. AS bonding lesson 12. So they're all there. AS bonding lesson 11. In terms of unit 2, the problem is I probably ought to box them. There's redox, which is part of unit 2. And energetics, there's energetics from unit 2 for you as well. So yeah, if you have a look through them, you'll see they are numbered. I don't know if you can, if I just typed in AS, I don't know if I can, oh, so I need to search my, that doesn't help me at all. Can I search my own channel? I have no idea. I'm not big on that one. AS. There we go. So, oh, there's AS calculations. I have boxed those off. I've put that in a playlist. Oh, blimey, didn't mean to do that. And then AS organic mechanism over, these are like revision. And then, right, there's the calculations in order. And then, yeah, you'll find others that have numbers. So introduction to organic, there's AS bonding lesson 8, bonding lesson 6, bonding lesson 5. Yeah, so have a look through them. I've done webinars on most things now, really. If you want me to do any particular one, Sasha, please let me know. Just put a comment on one of my videos and I'll happily do a webinar on a topic you want. Yeah. So well done to those people in the class. By the way, this is glucose. Nice to do this. This is glucose. MR 180. I love that one. Whenever I'm watching darts, you see them get 180, and all I'm going is glucose. So I'm really sad. And then this is sucrose. Sucrose. There you go, which is actual household sugar. So the higher out of these, so methane, it'd be nice to actually look these up. Propane is definitely going to be the higher of the two. If I was going to, okay, I will look first. Cool, fab. So I think methane has been like minus 140 degrees Celsius, degrees C. And then propane's like, I don't know, like minus 40 degrees C, something like that. So much higher boiling point. I kind of want to look those up now. I hate it when I quote numbers and I don't know them. So methane boiling, minus 161. Holy moly, it is small. It's very, very, very small. Blimey. Look what now happens to propane. Propane, yeah, that's French for propane, by the way. So there's propane, minus 42. Nailed it. Nailed it. Not too bad. Not too shabby, Mr. Duncan. So that makes sense. So this one's definitely higher. Absolutely. Next one, glucose. Let's have a look at glucose. So glucose. Oh no, didn't want to do that. Hello. We want glucose melting point. Yeah, we don't really want boiling point. Glucose melting point. So that's 146. Wowza, look at that. Wow, 146 degrees Celsius. Yeah, now sucrose. It's gonna be higher. It's gonna be higher. I don't really want, no, I'm actually just gonna get rid of the boiling point. I just want the melting point. It's easier. 146, like it. Let's do now sucrose. 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 So 186. It's higher. There you go. Bigger the molecule, the stronger the WIMFS, the more energy needed to break them. Russian accent. It's not even a Russian. I'm sorry. I'm terrible at a Russian accent. Can't do it. Let's do another one. Just for fun. Fun. Number 3. That was question number 2. That was number 1. Okay, let's choose another one. Hello. Let's do. What about HCl versus HBr? Ooh. Woo-hoo-hoo! Now, guys, you're going to need your periodic table. Yeah. Which one? Higher MPT. These are all gases, so I'm going to switch to boiling point. Higher boiling point, question mark? So what I'm now going to do is a clever trick, because now I'm going to get you to work out the MRs of each of them. So hydrogen is bonded to chlorine. Hydrogen has an atomic mass of 1. Chlorine has an atomic mass of 35.5. The MR, the relative molecular mass, is equal to 36.5. Right. HBr, hydrogen is bonded to bromine. Hydrogen is 1, bromine is 80. So the HBr's relative molecular mass, or commonly done as MR, little r subscript. It's the same thing, by the way. Yeah. So the MR on that one is going to be 81. Right. Let's have a look. And I need to switch to boiling point because they're gases. So HCl, shouldn't do that. But minus 85, whoa, that's low. Hello, HCl. Minus 85 is very low. Minus 85 degrees Celsius. So it's going to be bigger. Hello, bigger. HBr. Boom. What? Oh, her boiling point. Oh, minus 66. Minus 66. It is higher. Yay. What about HI? What about HI? We could predict it. What's the change here? It's about plus 20. We can predict her 1 and 127. Yeah, so that's total. MR is equal to 128. It's interesting, isn't it? Because look at the gap as well. Fascinating. That has increased. So 81, calculator, 81 minus 36.5. The difference between those two is 44.5. The difference between these two, 128 minus 81, is 47. Ooh, very similar. So the H, well done for those people saying HBr. HI is higher. Jack, would you like to predict its melting point for me? That would be nice. Very nice. Very nice. Very nice. Very nice. Very nice. Predict it. I bet we can predict it. Come on, somebody give me a prediction. Give me a prediction. It's definitely going to be higher, but we can predict it. That's cool, right? How cool is this? You can guess melting points of point. Amazing. Jack says minus 40. Love it. Let's go for that. Yeah. Minus 45. Which one do you want, Jack? Which one do you want? Which one? Which one? Let's go for 45. I like it. Check it out. Check it out, lads. Check it out. Minus 35. There you go. Not bad. Not bad at all. Not bad at all. How cool is that? So the difference there is minus 35, minus 6, minus 6. Gives me a difference of 31 plus 31. It's a little bit bigger, isn't it? Because it was slightly large. There was a slightly larger difference between the two of them. So a slightly higher increase. But I mean, to be fair, I think 40 was a really good guess, Jack. I would have gone for 40 as well. So well done on that. I would have predicted 40 and got 35 and been very happy. Maybe 5 degrees out. That's a winner. I like it. How cool is this? You guys are predicting melting points based on MRs. This is amazing. Love this game. Let's do. Ooh, so that'd be quite fun, wouldn't it? So methane, ethane, double it and add 2. Propane, propane, 8. Butane, double it and add 2, 10. Pentane, double it and add 2, 12. No, hang on, I've gone mad. Yeah, no, that's correct, isn't it? And then C6H14. Yeah, right. This is going to be fun. So the melting point of methane we had was minus 161. And propane, forgotten already, minus 42. Minus 42 for propane. Right, so my question is, what's ethane? What are these ones? Predictions we can make. Let's do this one first. This is just me being crazy. I'm enjoying this game now, guys. What's ethane first, please? What would our guess be for that? So the MR of methane is, and it looks like this is a stick. It's nice to do some stick diagrams. Yeah, we know that carbon weighs 12, hydrogen weighs 1, 1, 1, and 1. The total MR is 16. Right, what does ethane now weigh? So ethane is C2H6. There we go. So now we've got 12 plus 12 plus 12 plus 12 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. So I don't know what that is. 12 plus 12 plus 6, 30. Right, and then propane, propane. Yeah, propane. It's got an MR of 44. I just happen to know that one. Don't know why I know that one, but I do. Yeah, that's 44. So the difference between, we could actually just split the difference in boiling point, couldn't I? The difference between these guys here is about 120. About 120. Split the difference, 60. I'm going to predict minus 100. I think that's very reasonable. Minus 100, that's my prediction. Do people agree with me? Masaru is on it. He agreed with me. What a winner. Let's go for ethane. Sup, ethane. Boom. Minus 90. Yeah, not bad. Within 10. Minus 89. That's not bad at all. Not bad at all. Right, next. So what could we now do? So the difference between this guy here is minus 89, minus 161. The difference here is 72. Then we get minus 42, minus 89. The difference here is 47. Well, is there going to be a trend? Yeah? Well, there's still going to be quite a big difference. It's interesting, isn't it? That's a very good question, that. Butane, I know butane's boiling point. It's 0. Butane's boiling point is 0 degrees Celsius. So that has a difference of 40 as well, 40. So we've gone from 72 to 47 to 40. I feel like there's a trend happening here. So I'm going to now say that this one's going to have a difference of maybe 30. So I'm going to guess. Now, I have no idea what these are. Pentane, I'm going to say 30 degrees Celsius. And hexane, 60. I think that's reasonable. Yeah, I'd say that's reasonable. I've no idea. What's pentane? Haven't got a clue. Pentane. 36. I like it. So then hexane. 70. I like it. Cool. It's going well. I saw some of your videos and they are so useful. You explain very well. Thank you so much, sir. I hope you don't miss any other live lessons. You're very welcome, Sasha. It's such a lovely comment to make. Thank you. I really, really appreciate it. Sasha, if you need me to do any videos on any topic that you need, that you're really struggling with, as I said, post a comment on any of my videos. It'll come up on my feed for me, and I'll happily run one for you. More than welcome. More than welcome. What a lovely compliment to get. Really appreciate that. Right, year 10s, that brings me to the end of my lesson today. Let's just check our learning objectives, just for fun. So, we can understand that the larger molecules have stronger WIMFS, and we can now predict melting point and boiling point trends. How nice is that? That's super cool. I am really, really happy with today's lesson, folks. Can I say thank you so much for everyone who attended? I really, really appreciate it. I'll bring you guys back to me. It has been an stop share. There we go. I hope you guys have a lovely rest of your day, and I'll see you all very soon. Take care, guys. Bye.